So now let's go ahead and look at the second example of two-stage completion methods. And this is going to be the one that performs a logical OR. And there's a couple of different variants of this. We're going to look at one of them. This is the except either method. And this particular completion stage method will be triggered when either of two previous stages complete. So we're going to use two completable futures, which are going to be running asynchronously in the background. And whichever one finishes first, we're going to pick that one. And then that's going to take the result that we'll continue to process. So you can basically have a view in your head of a logical OR operation, logical disjunction, where the consumer action that's passed in here will handle either of the previous stage's results, whichever one finishes first. Once again, there's a pair of completable futures here. One is the future that's used to invoke except either, and the other is the future that's passed as a parameter to except either. And as before, it doesn't really matter which one is used to invoke it, which one is passed as a parameter. They both could be used interchangeably in either role. Except either is a bit like except or then except in the sense that it returns a future to a void or a completable future to void. So that means that there is in fact no meaningful return result that comes back, and your consumer action needs to have whatever side effect it is going to require in order to carry out the computation in a way that's semantically meaningful in the context in which it's applied. So as a consequence, we often use except either at the end of a chain of completion strategies, much like we would use then except at the end of a chain of completion strategies, except there's not going to be two chains that we're bringing back together again. So this particular example is really fun, and we'll see this example a little later when we do some deep dives into some case studies. But basically what this is going to do is it's going to start doing asynchronous sorting operations. So we're going to have one completable future called quicksort F for quicksort completable future. And that's going to supply a sync call to perform quicksort on some list. And then in parallel, we're also going to apply merge sort on some list. So we're going to end up with a quicksort completable future and a merge sort completable future. Both of those computations will run in parallel in different threads in the common fork join pool. Now, why on earth would you want to do this? Well, as you undoubtedly recall from your data structures or algorithms courses, whichever one covered sorting, quicksort and merge sort perform differently depending on the organization of the data. So, for example, certain methods perform better if the data is almost sorted, and so on and so forth. So it's not always clear at face value which of these two methods is the one that's going to run faster, quicksort versus merge sort. So as a result, rather than sit there and perform some convoluted analysis of algorithmic time complexity and count the number of instructions based on the input, that's so old school. Let's take advantage of the fact that we've got all these cores at our disposal, and we'll simply run both methods simultaneously, and we'll pick whichever one comes back first. And then we'll take the result and use that for the subsequent computation. So in this particular case, keeping in the spirit of leveraging all the cores available on our platform, we're going to have quicksort completable future dot except either, and we'll pass in the merge sort completable future. And whichever one of those computations finishes first, then we're going to perform some result. Now, or some action on the result. Now, here's an interesting little trivia. The completable future that finishes second actually is not canceled when the first completable future finishes. So it continues to run, except its result will simply be ignored. And the reason why the semantics work that way is that we don't know when we call except either if there's some other part of the code that may care about the results of the completable future operation that took longer to run. So we don't want to cancel it unilaterally just because it didn't get finished first. Somebody else may care about the results, but we're not going to care about the results in the context of except either. What happens in this case is we take the results, which as you can see here would be a sorted list, and then we're going to go ahead and print out the results of that sorted list in sorted order. So in this case, we're going to print out each element in the list in a mixed string format. But the key point here is not how we handle the result, although that's kind of cool in its own right. What's really interesting here is the fact that the result action depends on whichever completable future finished first. So that's the end of the discussion of the two-stage completion stage methods. So we looked at the one that handled the combination, the logical ANDing. We also looked at another completion stage method that handled logical ORing. And you'll find that they're both very useful under different circumstances in order to be able to perform various kinds of reduction operations on chains of completable futures.